Often when we think about building fluency and building strategies for fluency, there's a lot of focus on the arithmetic strategies, strategies for adding, subtracting, multiplying, and dividing numbers. And in 6th and 7th grade, we start to see in the standards sort of the culmination of those expectations, where in 7th grade, students are expected to add, subtract, multiply, and divide with rational numbers with procedural fluency. However, that doesn't mean that by 7th grade there are no more expectations in the standards around continuing to develop fluencies. And even with arithmetic fluency, we know that as a 6th, a 7th, and 8th grade teacher, and even beyond, there are still opportunities to help students develop and refine those skills for adding, subtracting, multiplying, and dividing all types of numbers. But in the standards, we see an emphasis start to build in 6th and 7th grade. This video is going to look particularly at something that happens in the 7th grade standards around other types of fluencies that are equally important. We start to see an expectation that students fluently use formulas, most of them for geometric concepts, but there's also some other measurement formulas that students start to learn in 7th, 8th grade and beyond. And so in this video, we're going to look at some strategies for finding the area of a trapezoid, as well as the formula, but also why the formula looks the way it looks. When we think about many quadrilaterals, trapezoids have a different formula than most of the other quadrilaterals. So why does the formula exist the way it is, and what are some other strategies? Just like when we build fluency for arithmetic strategies and operations and we build number sense, we don't want to just get the answer for accuracy's sake and for efficiency's sake. Though those things are important, we also want students to be flexible, and we want students to base all of that on a real understanding of what's going on. And so that's the purpose of this, looking at the area of trapezoids, some strategies that will build understanding, and then also some ideas for helping students understand why the formula looks the way it looks, and students might even be able to derive a version of the formula that we could help them turn into the sort of conventional formula for the area of trapezoids on their own. So first, we're going to stay away from the formula, and we're going to think of it more like composite figures. We're going to break them apart using what they know from previous grade levels, which up through 6th grade, they have worked now with rectangles and other parallelograms, as well as triangles. So if we can decompose these into rectangles and triangles, we can find the area without having to have the formula. And that's going to be the basis for our first strategy. So I have 3 different types of trapezoids that students might run into. So a trapezoid where we actually have a right angle on one of the legs of the trapezoid, an isosceles trapezoid, and then a trapezoid that is neither. So this is not an isosceles trapezoid. The legs aren't the same, so the angles aren't the same. And then here again we have the isosceles and the one with the right angle. And if we can make this strategy of decomposing work with all 3 of these, then students can build that understanding before jumping to a formula that they may or may not understand. So this first one, all we have to do, if we just look at this trapezoid, here's our right angle. If we see where it's given us the height and we just decompose that there, we now have a rectangle and we have a triangle. And students know how to find the area of rectangles and triangles by the time they're in the 6th grade. So in the 7th grade, this is something that we can expect students, or we can support them to do maybe a little more easily than jumping straight to a more complex or complicated formula. So all we need is the base and the height for the rectangle, and then the base and the height, which we'll divide by 2 for the triangle. So if I look at my trapezoid, I can kind of figure out separately, if we break them apart, what is the base and the height of the rectangle. And so might be tempting to think 12 because it's at the bottom, but 12 is the distance all the way across. I just need this distance, which is 10, and my height, which is 8. So 10 and 8, we get 80. And I intentionally picked some kind of easy numbers. The point of this is developing that understanding, not necessarily working on more complicated or complex arithmetic. And I'm not necessarily worried about units right now either. We're just thinking about the concepts and how we decompose and work with these. So the triangle, I also need the base and the height. And so my height is actually the same. The height is still 8, but I need the base. And so if I know, from here to here was 10, so this is 10, but all the way across was 12, then that's going to be 2. So we'll just do 8 times 2, which is 16, but then we have to divide that by 2 and 8. So now we've decomposed, we found the two parts, 80 and 8. The area for this one here is 88 square units. I'll go ahead and write that, 88 square units. All right, so let's look at now how this works with an isosceles trapezoid, because when we break apart that, one of those triangles off the side, we don't have a rectangle there. And so without that rectangle, we're going to have to think a little bit more. It's a little bit more complex. And so the sequencing here, like many things, is very important in the order that we present these to students. So I'll start with my isosceles trapezoid. I'm not going to worry about, I'll go ahead and mark that those legs are the same. I'm not going to worry about labeling anything yet. I just want to think sort of conceptually, how do I break this apart into things that I'm familiar with? And so we can't break it once. If I break it once like I did last time, I still have a trapezoid over here. But if I break it again, now I have two triangles and a rectangle. And again, I know how to find the area for all of those shapes. And that's what we need. If we're working towards the area, this strategy still works even with isosceles trapezoids, as long as we have all the information we need. So let's make sure that we have what we need. If I think about the rectangle in the middle, the base, because it's given to me here, I know is 18, and the height is 10. And in fact, the height I know is going to be the same all the way across, because the two bases of a trapezoid are parallel. So the height all the way across is 10. So 10 and 18, I know this here for the rectangle is 180. Now I have to think about the triangles, and there's a couple of ways that we could think about doing this. Because this is an isosceles trapezoid, this is only true with isosceles trapezoids, it won't be true with this one here. I know that this distance of the triangle, so this distance here and this distance here, the bases of the triangles are the same. Because since these legs are the same, I know these angles are going to be the same, and so that the assumption that those are the same is true. And if the base of the rectangle was 18 and then the base all the way across the trapezoid was 22, that's a difference of 4. So I know that 4, got to split that up between here and here. This is going to be 2 and 2. And then again, my height was 10, so 10 times 2 divided by 2, which is just 20 divided by 2. So the area here is 10. This is the exact same triangle, so the area here is going to be 10. And then we just combine 180 plus 10 plus 10. The area for this isosceles trapezoid is going to be 200 square units. All right, so for our third and final type of trapezoid, this is one that neither has a right angle or is isosceles, and so this is going to make the way that we think about it a little different. And so I'm going to go ahead and draw that best as I can, trying to really show that this is not isosceles. These legs are not the same, the angles are not the same. Now I'm going to start just like I did with the isosceles. I'm going to break it into 2 rectangles and 2 triangles, and then I'm going to go ahead and find the area of the rectangle. The base of the rectangle, I can use this side here to figure that out. That's 20, and my height was 7, and so the area of the rectangle is going to be 140. Now we've got to figure out the triangles. Like last time, I do know the height. The fact that this is not isosceles doesn't impact what the height is, because again, these two bases are parallel, so it's 7 all the way across. However, determining these distances might be a little more complex. The question is slightly different because these legs aren't the same. like they were in the isosceles trapezoid. So the difference between 20 and 30 is 10. So I know that somehow these are 10. It could be 8 and 2, it could be 9 and 1, it could be 7 and 3. I don't really know. And so calculating them separately isn't really possible to do accurately because I don't know how to divide those. I would need to know the distances of the lengths of the legs or maybe the angles, and we could use some trigonometric functions, which students aren't using in 7th grade, to figure that out. Or if we imagine that we kind of broke these two triangles off of the trapezoid. If we broke the two triangles off and then kind of put them together, we would end up with a triangle, a new triangle, that looks a bit like this. Now, here's why that matters. I don't know what this or this distance is separately. However, I do know that together they're 10. And because together they're 10 and they both have the same height of 7, I can create a sort of new triangle, either physically drawing it or just kind of mentally think of a new triangle that has a base of 10 and a height of 7. And I again know the formula for finding area of a triangle. So 10 times 7 divided by 2, so 70 divided by 2, this is 35. And so now I know the area of the rectangle, I know the combined area of the two triangles. I can compose those, put those back together, and I know the area of this non-isosceles trapezoid is 175 square units. So for all really 3 types of trapezoids that students are going to run into, where we have again the right angle, the isosceles, and then neither, where our legs aren't the same, and we also don't have a right angle, we can still use strategies sort of outside of the formula to build understanding around finding area of trapezoids. So even coming directly into 7th grade without direct experience working with trapezoids, students have worked with rectangles and triangles in 6th grade. They even worked with composite figures in 6th grade. And so thinking about this like a composite figure, we can continue to build that background and build that understanding for students. All right, now what about the formula? Because that is part of the expectation that students are developing fluency around using the formula. But just using the formula without understanding it isn't really developing fluency if there's not an understanding. And so what we'll do, and I'm going to use this bottom trapezoid here because of the 3, it's sort of the most complex. So if we can do this process using this trapezoid, then surely it'll work with really any trapezoid. So I'm going to draw the trapezoid again, trying to make it clearly look like it is not isosceles. And we're going to kind of play with this and manipulate it to show where this formula comes from. Now, the only other formulas that we know are rectangles and triangles. We know, and this is derived very early on in elementary school for finding the area of rectangles, and then it's formalized a little later that a rectangle, we just take the base times the height. And then in 6th grade, students learn that triangles, well, if we cut a rectangle in half, we have 2 triangles. So a single triangle is just the base times the height, but then we need to cut it in half or divide it by 2. Sometimes the formula is written this way. Either are the same. They're equivalent to each other. Now, a trapezoid, I want you to imagine that we took a rectangle and we cut it in half. Instead of from the vertex to the vertex, we cut it in half like this, where we actually have some distance here and some distance here. Now, imagine that we cut this perfectly so that this distance matched this distance and that this distance was the same as this distance. If we did that from the rectangle, we have created 2 perfectly even, 2 two trapezoids with the same area. So that's one of the first parts of the understanding, is that we can create a trapezoid using half of a rectangle. We could even do it using half of a parallelogram, and this is going to look a little more like an isosceles trapezoid. If I were to cut here, I've now created two. If this distance winds up being the same and that being the same, I've created two isosceles trapezoids. If it's not quite perfect, then I've just created two trapezoids, sort of like this one here. Now, the formula is going to have to be a little more complex than a triangle, because with a triangle, we didn't change the base and the height. The base and the height stayed exactly the same. However, with our trapezoid, these distances stayed the same. When I cut this line, it didn't change. It didn't change that. It didn't change the heights. And we can imagine the height of the parallelogram being here. We didn't change the heights, but we did change the bases, because we cut through where the base is. So we have to think a little more sophisticated to put this together. So I'm going to start with, go back to this trapezoid. Now imagine that I added another identical trapezoid, but sort of upside down right next to this one. And building off of this idea that we can create two trapezoids by cutting a parallelogram or rectangle in half, let's create a parallelogram by doubling the trapezoid. Now, we said that we know the height isn't changing, right? So area, I'm not changing anything about the height. So I'm still going to have h in the formula for height. However, the base is different. So if I think about the parallelogram, this distance across here, this is the base. That's the base of the parallelogram. But where does that come from? So we have this distance here from the trapezoid, and then because we flipped it, we have the distance from the other side of the trapezoid, and this is formally called base 1 and base 2. So when I flip it, now I have base 1 up here and base 2 down here. So my base comes from adding together base 1 and base 2, and then of course we already established that the height doesn't change. The height of the trapezoid is the same as the height of the parallelogram, so we'll just multiply that by height. Back up to where we started this conversation, we were able to make the trapezoids by cutting parallelograms or rectangles in half. So just like the triangle, we're going to need to account for that, and so we can either write it like this with a 1/2 in front, or sometimes, just like we can write the formula for a triangle a couple of different ways, we could say base 1 plus base 2 times the height over 2. We can show the formula for a trapezoid either way. And so when we're thinking about fluently finding the area of trapezoids and fluently using the formulas, just like when we build numeracy and number sense, we want to make sure that students are basing it on an understanding of what's going on and what trapezoids are and how they work and how we can use different strategies to find their areas, but then also understand where the formula comes from, and then we can start to fluently use and apply the formula for area of a trapezoid.